Kia ora koutou, nau mai, haere mai. Welcome to lesson 15 for introductory physics. This is going to look at power and machines. So we've introduced work, we've introduced energy. We're now going to introduce a new concept called power. The goals for today are to define and calculate power, use the conservation of energy to explain mechanical advantage, to define the efficiency of a machine, and to explain why efficiency is always less than or equal to 1. Firstly, defining power. Power brings into account the time it takes to do work. We ignored that when we talked about the work. We talked about the work being force times distance, and we said if you take an object up a ramp or you lift it straight up, then you do the same amount of work. But what we ignored was the time it took to do that. Power is the rate at which work is done. So it's the amount of work done divided by the time taken to do it. We use the symbol capital P for power. So power P is equal to W over delta T. Remember delta being change in, so the amount of work done over the change in time. The units for power is joules per second. Joules is the unit for work, seconds being time, joules per second. But this is so common that we give it its own unit, and that is the watt, W-A-T-T. And we use the symbol capital W for the unit watt. Now you need to be careful there because work, we also use the symbol W in the equation, whereas here power has the symbol W for its unit, but power is calculated based off work, which has W. So you do need to be careful of that. We do get quite a bit of repeating letters and symbols throughout physics, and you just need to be confident at keeping track of everything. Again, that's another reason why you need to do the physics first. You need to make sure you think about the scenario, think about what's going on in a system, because if you just rely on the maths, then these sorts of repeating symbols mean that it's easy to get confused. Work and power are closely related, and they can often be confused because they are quite similar. The work is the amount of energy used, or amount of energy converted or transformed, however you want to define it. Power is the rate at which that transformation or that application of energy occurs. An example is to think about a litre of petrol. Combusting petrol is the process of burning it and turning it into usable energy, so spinning a motor or usually spinning a motor or some other function. Combusting that 1 litre of petrol will provide a certain amount of work. The amount of work it provides is determined by that petrol, by its properties, by what happens when you combust it. How quickly it does the work determines how much power is produced. So it might still produce the exact same amount of work in 2 different engines because it's the same petrol, it's got the same chemical properties, and it can produce the same amount of energy when you burn it. But the rate at which the engine burns that petrol determines the power. So if you decrease the time, you get an increase in petrol. So if you put that petrol into a lawnmower, then that lawnmower has a small engine, burns a small amount of petrol every time, every little cycle that it does in order to spin the blades of the lawnmower, and it might take a couple of hours to chew through that litre of petrol, in which case the power is quite low because that amount of work done was over a whole hour. But if you put it into a car, especially a high-performance one, that might do the work really quickly. An average car might use a litre in 15 minutes. A high-performance one might use that in a minute or two. And then the power is going to be a lot greater. The total work that came out of that 1 litre of petrol, the amount of energy released by combusting it, would be pretty much the same. There are small things about efficiency, which we're going to talk about. But in general, the amount of energy that comes out will be pretty similar. But the quicker you do it, the quicker that energy is released, the higher the power. The word power is another one of these words that we have use for in everyday life, but we also have a specific definition for in physics. I'm not sure why I said specific, weirdly, but we have a specific definition for it in physics, and you need to be aware of that and make sure you're not getting confused about what we mean by power. In everyday life, when people talk about power, one of the most common uses is just a plug on the wall. You know, give me some power, plug in the computer. I need a power on the computer. Power in that sense is talking about electricity. Even then, it's not really used in the correct physics sense usually. We'll talk about electricity briefly later on in the course. But there are many more uses of the word power. We might be talking about social, business, economic, governmental, military, etc. All of those have different uses or ideas behind the word power. So it's actually, in some respects, it's easier to forget that you've met the word power before and just think of it as a new word that happens to also be power. Right? So power here is the rate at which energy is applied, the rate at which work is done. The next part of this is going to look at machines. So a machine is simply a device which changes the input force in some way. They might multiply it, they might change the direction in which it acts, or they might do both. They cannot create or multiply work or energy. Remember, conservation of energy says energy can't be created. Work is just energy, so we can't just create energy in a machine. All a machine can do is transform that energy. That's all we can do. That means that the work output must be, at most, the same as the work input. It might be less, but at most it would be the same as the work input. As a formula, if we're talking about forces and distance, which is what we're going to be dealing with today, because that's the sort of energy that we've met already, then the work out is going to be equal to the work in. So force in times distance in is equal to force out times distance out. Work in equals work out. The very simplest machine, or possibly one of the two simplest machines, but in this case, the simplest machine is a very long object put over a pivot point. That pivot point we call a fulcrum, F-U-L-C-R-U-M, a fulcrum. And if you apply a force to the long end of the lever, it will move downwards a lot more than the short end will move upwards. But since the work output is equal to the work input, if we make the output distance smaller, we must make the output force bigger to keep that equation true. Because if we just made D out smaller and kept F out the same as F in, then the right-hand side of that equation will be a lot smaller than the left-hand side. So in order for that equation to be true, for the work out to be equal to the work in, then decreasing that distance means we must be increasing the force. Suppose the end of the lever goes down 1 meter and you're applying a force of 10 newtons the whole way down. The short end only moves up 10 centimeters, then how much force is applied to the object on the other end of the lever? So what's the upwards force? You'll notice that not only is this changing the magnitude of the force, it's changing the direction. Here you're pushing downwards on the lever, so the force is downwards, the displacement is downwards. For the outside, for the small end of the lever, the displacement is upwards and the force is upwards. So we're actually changing the direction and the magnitude of the force. So the short end goes up 10 centimeters, the long end goes down 1 meter. So we know the input, 10 newtons across 1 meter is 10 joules. We're putting in 10 joules. That's the work put into the long end of the lever. So the short end of the lever must put out 10 joules, but it's doing 10 joules and it's only traveling a distance of 0.1 meter now, 10 centimeters, 0.1 meter. So that means the force output is going to be 10 divided by 0.1, work over distance, 100 newtons. So we put in a force of 10 newtons and we get out a force of 100 newtons, which is actually really useful. It means we can lift things that are a lot heavier than we otherwise would normally be able to lift. The cost of doing that is that we can only lift them a fraction of the way that we would if we were lifting them as far as we pushed the lever. We pushed the lever down 1 meter and we only had to push down with 10 newtons. That's the equivalent of the weight of about a 1 kilogram object. In response, we got to lift something that was about 10 kilograms, but we only got to lift it 1/10 of the way. Excuse me. So the cost of doing that is a decrease in the distance, but we get the useful result of an increase in the force. The other simple machine, the reason I said that it was one of them, is this one, the pulley. The pulley is another simple machine. The simplest pulley, which is just the one shown, we have a wheel with a rope going over it. It just changes the direction of the force. It doesn't change the magnitude at all. It just changes the direction. The distance in and out is exactly the same. If you pull the end of the rope towards you by 1 meter, then the mass, the object on the other end, is going to be lifted up by 1 meter. The distance doesn't change, but it allows you to change the direction. So it might be really difficult to lift an object straight up for 10 meters, but if you've got it hooked over a pulley, you can just pull on that rope until the rope has come towards you by 10 meters, and therefore you don't actually have to move. You can just pull the rope by 10 meters. So the pulley is more, the single pulley like that, like the one illustrated, is most useful in terms of just changing the direction and allowing it to be simpler to lift an object. You still have to be able to apply enough force to lift it because you're not changing the magnitude of the force, but you can lift an object a distance or in a location that might otherwise be difficult. However, you can change the force with a pulley. You don't have to do it the way that we had illustrated on that previous slide. What you could do is the example shown here. You hang the pulley off the object, so the pulley comes straight off the top of the object, the rope is attached to the ceiling, and then you lift upwards on the other end of the rope. If you lift that end of the rope, the one where it says F in, if you lift that upwards by 1 meter, then the overall length of the rope hasn't changed, and the object will have only gone up 1/2 meter. It might take you a little moment to think about that. So if you need to get a little diagram, get a bit of paper and a pen, sketch it out. If you pull that rope upwards by 1 meter, the object is only going to go up by 1/2 meter. The distance is going to be halved. And that's because the length of the rope hasn't changed. Actually, I'll do that now for you just to be hopefully really clear, because we are going to do a little bit more on pulleys after this. So I'll just draw this quickly. So hopefully you can now see everything. If we have this as our rope, and here's our pulley, we've got this rope, and we want to pull this up by 1 meter, then what that has to do is it has to take 1/2 meter from here, and 1/2 meter from here, and lift the whole thing up by that 1/2 meter. So this goes up by 1/2 meter, and that, so it's not actually taking 1/2 meter of rope from here and from here. It's obviously just pulling the rope up, but you can think about it that way, that you've taken 1/2 meter off here and 1/2 meter off here in order to pull this end up 1 meter. So that means that the overall height has gone up by 1/2 meter, even though you pulled the rope by a whole meter. So hopefully that makes sense. Again, just get a pen and paper and draw some sketches and think about it until you're confident that you agree with me on that statement, because it's true. If you pull that rope up by 1 meter, it will only go up by 1/2. So it halves the distance. As we just saw with the lever, if you decrease the distance, you must increase the force. So if we halve the distance, we are doubling the force. So you can now lift something twice as heavy as you would normally be able to by using this pulley setup. And you can actually repeat this using multiple pulleys, not just a single wheel, but using multiple wheels and looping the rope around lots of times. So here's a question. What is the output force if we use 50 newtons on the end of this rope? We've got 4 wheels now. We've got 4 wheels, and we want to figure out the output force here. I do recommend you have a go at this question. Don't just sit there and wait for me to give you the answer, which I am about to do, but do have a go. Pause the video if you need to. Think about this question and try and figure out what the answer is going to be. We have to use the same process as we just did before. Figure out that change in distance. You have to figure out how much the object will actually go up for every unit of distance that you pull the end of the rope down. As we saw with the single pulley, the one we just saw where the pulley was attached to the object, when you pulled the rope by 1 meter, the object went up by only 1/2 meter. So how far will this object go up if you pull this rope down by 1 meter? Again, you need to think about how much each of these different legs of the rope would decrease if you pulled this end down by 1 meter. If you pull this end down by 1 meter, then each of these is going to have to give up 1/4 meter. Sorry, that mouse is just going back a slide for me. Each of these little bits of rope is going to have to lose 1/4 meter of length in order for the end one to gain 1 meter overall. So that means that you're only getting 1/4 of the distance, so you would get 4 times the mass, 4 times the weight force. And you could lift something that is 4 times as big as you would normally. The way I've drawn this pulley system with all 4 pulley wheels all separate and big and clunky is not how these pulley systems are normally designed. They're normally far more compact. They'll put the wheels right next to each other and overlap each other. As you can see in the background, hopefully you can still see the slide background a bit there. You can see there's a double pulley wheel with ropes going in, 2 ropes going in. That's just a double pulley wheel that is combining 2 of these wheels all together. The next part of this lesson is on efficiency. So this is the bit where I said, assuming we don't lose any energy to friction or any other places, any other energy loss. We don't always have that being true. We know that machines can't increase the work done. We can't create energy. We can't put in 100 joules and get out 1,000 joules. That would break physics, it would break everything. So we can't increase that energy, but we can easily lose energy. If there's any friction, if there's anything else going wrong, then some of the energy you put in will be lost to other forms of energy. It won't all be useful output work. Getting a machine that's 100% efficient is not really practicable. It doesn't really happen. You always get slightly less than one, but some machines do get very close to one that we can actually sort of round up and say that they are pretty much one. So if we lose some energy, then that means that we're not going to get all of the energy out that we put in. The amount of energy we get out compared to the amount of energy we put in is what we call the efficiency. So that useful energy output divided by the total energy input. Obviously, if you counted all the energy output, that would include the friction and all the other types of energy that we lose. So the heat and the sound and the light in some cases when you get sparks and things. But you would, if you're counting all the energy output, then that would obviously be equal to all the energy input. So instead we specify useful energy output. So how much energy are you getting out that you wanted from this machine, the purpose of the machine, versus how much energy you had to provide to put into that machine in order to get that useful energy output. So you might have to put in 100 joules to get out 95 joules. In that case, the useful energy would be 95, the total energy would be 100, 95 over 100 is just 95%. So the efficiency is just how much actually, it tells you how much actual energy you have to put in to get out the energy you want. There's a slightly different example from the one I just gave you. If you put in 10 joules of work and you only get out 9.8, that would be 98% efficiency. Hopefully you're all familiar with percentages. Do stop and have a look at percentages. Refresh yourselves on those if you're not familiar, but that's, you will need to use the percentages for efficiencies. Whenever we transform energy from one form to another, we always lose some of it to thermal energy, also to sound and occasionally light. But there, as I said, you can get machines that are very close to perfect efficiency. You cannot actually get one that's perfectly 100%. They can get close though. But that means that the amount of usable energy is always decreasing with every transformation. Eventually, there'll be nothing left but thermal energy, and that's not very useful for doing work. So eventually the entire universe will just be thermal energy. There'll be nothing else left. Recycled energy is talking about taking some of that energy, that thermal energy, and I said we can't do much work with that, but it doesn't mean it's not useful. If we can make sure we heat up a specific part of our system, we might actually want that. For example, when you're in a car, the engine is not terribly efficient. Car engines are not the best efficient, most efficient engines we have. But they do produce useful recycled waste energy, useful waste energy that we can recycle, which is not really recycling, it's more of a reusing, a repurposing. And you take that thermal energy and you pump it into the car, and then you can heat up the occupants, you can make them a bit warmer. There are older power stations, which I believe there are still some in use, mostly in the United States, but there may be others. And what they would do is they'd do the same sort of idea, but they would actually pump that waste energy as steam into nearby buildings to provide heating for those buildings. That was cheap because it was essentially just this waste energy that otherwise would have been just let off into the environment. And instead they sort of captured it and transported it into buildings to provide heating for those buildings. So there are ways to catch some of that, and it can end up being sort of semi-useful, even if it wasn't the original purpose of the machine. This last part is kind of a sidetrack. There's nothing too critical here, nothing that will stop you progressing with the course, but it certainly is some interesting information. And that is, the source of all our energy on Earth is the sun. Well, that's it. The sun is the primary source of energy for everything on Earth. There is sunlight coming to Earth from the sun. We're going to talk more about sunlight when we meet light waves and vibrations later on in the course. That sunlight hits Earth and the plants absorb it. The plants trap that solar energy and they convert it to organic matter. That's what photosynthesis is. It's plants capturing that sunlight, which is energy. We'll talk about energy in the form of light later on. But sunlight is just energy being sent by the sun to Earth. And the plants capture it. They store it inside their cells as chemical energy. They build starches and other molecules and things and store it inside their cells. So we now have energy in these plants in a form that we can access, and we do. We access it as food. Other animals access it as food as well, and we also access it as fuel because plants that die turn into things like coal that we can burn and access the energy later. So plants get all of their energy from sunlight, mostly. Biological energy, when we eat something, right, we turn energy that we get from plants or other food sources into energy that we store in our own cells, so that then we can use that to do physical activity and motion, but also to power our vital organs and keep us alive. A very simplistic example from the textbook: you may take 10 kilograms of grass to produce 1 kilogram of gazelle, and then 10 kilograms of gazelle to produce 1 kilogram of lion. That decrease in the useful energy is that same idea of inefficiencies, but now we're talking about biological machines. Living organisms are essentially biological machines. They take energy in and they convert it to energy out. We take energy in the form of plants or food, and we get energy out in the form of being able to move and run around and push things and lift things. So every time that you consume food, you're actually losing a bunch. So it's a very inefficient process. Solar energy also causes weather patterns. We have water evaporating because of the energy from the sun hitting the water, and it evaporates, goes up into the sky, into the atmosphere. That then condenses into clouds, and it rains, and rain falls down onto the ground, and that runs down in rivers and so on as flowing water. We can access the energy of that flowing water by building dams or water wheels and convert it into mechanical useful energy like spinning a flour mill, things like that. Solar energy also causes air to heat up, and when one part of the air is hotter than another part or colder than another part, then you're going to get air flow, and air is going to move, and that's what wind is. Wind is just the motion of the atmosphere due to temperature differences. So solar energy causes all of our wind patterns, and we can capture that by building wind turbines which spin as the air moves past. So we can capture the sun's energy indirectly through weather, or we can capture it indirectly through plant matter. Obviously, we also get solar panels, which capture the sun's energy directly through heating the object that we put in front of them. There are other sources of energy. The sun is the primary one for Earth. It is where most of our energy does come from. But we do get a small amount from tidal energy. The rotation of the moon around Earth causes the Earth's surface water to ebb and flow, and that is our tide system. So there is some energy there. There is also nuclear energy from the nuclei of atoms. Although, as we'll learn later on, heavy atoms are made in stars anyway, so not our sun, but they do come from other stars. So that energy does come from other stars as well. And geothermal energy from the high temperatures inside the Earth's core, which is actually from gravity and nuclear energy. So gravity pulls all of that matter together, forms the planet, and then all of those things get really hot and release some of that energy that's stored inside the nuclei of the atoms, which, as I said, comes from other stars anyway, as we're going to get to. So none of that is going to be tested or checked on right now, although it will be relevant to other parts of the course that we'll see later on. So we will sort of link back to some of these concepts. So it's worth understanding and following through this little bit of the lecture, but as I said, there's nothing critical that you need to remember right now from this. And by that, I just mean that last part, the part about sources of energy. You still need all the other stuff. So there's the review of everything off this lesson. In the next lesson, we are going to look at, I actually can't recall what we're going to look at. I'm just going to double check. Next lesson, we're going to move on to momentum. That's right. We're going to look at momentum, which is not energy. It's something else. It's a new concept, momentum. The idea of looking at that, though, is that we can then bring in collisions, which will look at energy and this idea of conserving energy and combining it with momentum and looking at collisions and how things behave when they collide with each other.